Hi, it's time for integrations of complex variables. This is the seventh time. The title is Multiplication and Division of Power Series in section 73. Before looking at the main part, we would like to review section 71 briefly. Integration and differentiation of power series. There, we have learned that a power series summation from n equal to 0 to infinity an times g negative g naught to the n represent a continuous function denoted by s of g at each point interior to each circle of convergence. Here, look at. Here is the center of the circle, G naught, and the radius of this circle is R1 here. Okay. Then interior to this circle, we have a complex number G here. We can compute S of G by the power series given by this. According to theorem 1, on page 213 and corollary on page 214, the sum S of G is actually analytic within that circle. Okay, this is amazing. So you must remember these two results. Okay, now we take a look at multiplication of power series. In this time, we are talking about multiplication of power series. Suppose that each of power series given by this expression 1, the first power series is given by this using coefficient an, and the second power series is given by this using bn as coefficient, converges within some circle defined by absolute value of g negative g naught is equal to r here. G naught is the center of this circle and r is the radius of this circle. Their sums f of g and g of g respectively are then analytic functions in the disk defined by this. Just you look at here, because in section 71, we learned theorem and corollary just before we reviewed them. And the product of those sums has a Taylor series expansion, which is valid there. That is, in the disk given by this, absolute value of g negative g naught is less than r here. So f of g times g of g is equal to summation n is equal to 0 to infinity some coefficient cn denoted by cn times g negative g naught to the n, where the circle, a circle of convergence here, given by this. Absolute value of G negative G naught is less than large R. According to theorem 1 in section 72, the series 1, okay, I mean here, the two series are Taylor series. Hence, the first three coefficients in series 2, which means the product of f of g and g of g, are given by the equations by using Taylor series of f of g and g of g. Okay, here is the Taylor series for f of g, and this is a Taylor series for f g of g here. Then you just expand the terms, each term, then you get this. Here Cn, okay, represent coefficient of Taylor series for the product of f of g and g of g. Cn can be computed by, like this. For example, C sub 0 is equal to f of g naught times g of g naught. Because f of g naught, here you can see f of g naught is a0 here. And g of g naught is b0 here. So c0 is equal to a naught and a naught times b naught. C1 is computed by this formula. C1, okay, let's check it. C1 means n is 1. So here n is 1, which means the order of this term is 1, in terms of variable g. So we need that terms of order 1, I mean degree 1 here. That can be made by two cases, this and this. First comes from compute by multiplying f of g and g prime g of 0. Okay, f of 0 g naught, f of g naught comes from the constant in the first power series here, which means this. Sorry, this is f of g naught, because and then in the second Taylor series there is g prime of g naught is the coefficient of the second term here, the degree 1 polynomial here. So this would be has the degree 1. This is the coefficient of the term of degree 1 here, and the second is also has comes from the terms of degree 1. This is the coefficient of the term here. F prime g naught comes from this here, and the g of G naught, yeah, comes from here. So product means, yeah, this is the coefficient of, yeah, G negative G naught. Yeah. Okay. To the power of n, we can omit here. So this is the first, yeah, the term of degree 1 in the expansion of this, which is equal to a naught times b1 plus a1 times b naught. Okay. Here, yeah. Here we use this notation for each, yeah, Taylor series. Okay. Okay. C2 can be computed in a similar way, but we need to consider 3 cases because 2 can be divided by can be computed by 2 terms by 3 cases. The first case 2 plus 0, and the second case 1 plus 1, and third case is 0 plus 2. Okay. These cases, yeah, are only cases for to compute 2 by adding 2 terms here. So for each case, we compute, yeah, how many cases there are when we compute product, yeah, where each term comes from each, yeah, expansion. Then we can write this. So f of g naught times g double prime of g naught plus 2 f prime of g naught times g prime g naught plus f double prime g naught times g of g naught divided by 2 factorial, which, yeah, is equal to, because this is a naught, we use this notation when n is 0, which means constant. Actually, yeah, it's the same to f of g naught, and this terms comes from, yeah, this, because bn, yeah, involves the second derivative of g here in the Taylor series expansion. So g double prime g, yeah, of g naught here, and then these terms comes from, yeah, a1 and b1, and f double prime of g naught times g of g naught, yeah, which is equal to a sub 2 times b, yeah, naught here.